Okay, good morning. So we also continue our lesson about matrix multiplication. So we learned that the property of commutativity is lost, but so that is the main difference between. So let us review. There were three important differences between matrix algebra and number algebra. Do you remember those? Yes? You don't remember anything at all? So the main difference is that usually always A times B as numbers are defined, but there is no guarantee that matrix multiplication is defined, and even if A times B is defined, there is no guarantee that AB is equal to BA as matrices. That was one important difference, of course, the main important difference. What was the second one? Any clues? Yes?
Maybe like if they were in parentheses, you can multiply them. Like if you got two matrices in parentheses or numbers, you can multiply them like normal. So I don't know what that's called.
Associativity is preserved.
Well, how did that work?
Yeah, I want to. Yes?
Isn't it that two non-zero matrices can become a zero matrix?
If you multiply them. So that is, there is no zero product rule. If A times B as matrices is equal to the zero matrix, there is no guarantee that each one of them should be at least zero. Okay? So what was the other difference? So this is this part of this lesson, yes. And that was, the other one was the cancellation. Is not whole. Yeah, if A times B as matrices are equal to B times A, yes. So where was it in the notes? Yeah, here. So here you see that if A times B is equal to A times C, even if it is guaranteed that matrix A is not the zero matrix, but still you cannot conclude that B is equal to C. Yes, and I told you that there are some exceptions that we will study later, that if A has another property, not A not equal to zero, if A has another property which is called invertibility, if A has that property, of course, then you can cancel A from both sides and conclude that B is equal to C. So here, for example, if you go and watch the video, you will see that this was an example that AB is equal to AC. If you calculate A times B, you get the same matrix as if you calculate A by C, but as you see, B and C are quite different matrices. Okay? Then, of course, I gave you this example. I asked you to show that this matrix has this property that if AB is equal to AC, for this particular matrix, then you can cancel this A from both sides and conclude this. So that was the last example we did. And then I summarized the differences, which is actually important. So the whole important thing of matrix theory is this summary that you need to know, okay? So the product of every pair of real numbers is always defined, but this is not guaranteed for any pair of matrices. And then A times B as numbers is always equal to B times A, but there is no guarantee that even if AB and BA are defined both as matrices, there is no guarantee that they are the same. The zero product rule in general does not hold. If A times B is 0 in numbers, I can conclude that either A is 0 or B is 0, yes? But if I have A times B as matrices equal to the zero matrix, there is no guarantee that either one of them should be the zero matrix. And then last thing is that if I have AB is equal to AC, and if A is not equal to 0, I am allowed to cancel A from both sides and I conclude B is equal to C, but this is not guaranteed when it comes to matrices. Yes? Is that clear? Okay, so these are the differences. But now today we want to talk a little bit about similarities, okay? So the first theorem is probably understandable for everyone. If I have a matrix and I multiply it by the zero matrix, what will happen? Definitely it becomes a zero matrix. But of course you have to match the orders. So if I have a matrix M by N, if I want to multiply it from left to a zero matrix, that matrix should start with an n. Yes, and then of course the answer will be a zero matrix, but a zero matrix of order n by p. And then if you want to multiply it from the left, the zero matrix that you multiply from the left should contain exactly n columns as the number of rows of this matrix, but still the answer is again the zero matrix, but the zero matrix n by p. But if A is if a square matrix, and A0 is also the zero matrix of a square matrix of the same order, then of course it doesn't matter. If you multiply A by 0 or 0 by A, the answer is always the zero matrix. So we can say that every matrix and the zero matrix commute, yes? If of course they are of the same order. So these are very simple examples. So you see that I have taken any matrix that I want, I just multiply it by the zero matrix. This becomes this zero matrix. Why? Because this contains 3 rows. So this is 3 and 2 columns, 3 by 2. The zero matrix that you see here is 2 by 4. Is it possible to multiply them? Yes, because these two numbers are equal. And what will be the answer? It will be as the zero matrix of order 3 by 4. And then you see that I have written the zero matrix of order 3 by 4. So then you can immediately see the other examples. So if I want to summarize that, this means that if you have a matrix multiplied by the zero matrix, the answer is the zero matrix if it is possible to multiply it. Yes? Okay, and the next thing is this very important theorem, multiplicative identity. So this is why I told you that these identity matrices play an important role in matrix theory. And this is because of this. These are multiplicative identities. What do I mean by that? It means that essentially when you take a matrix and multiply it by the identity matrix, the answer becomes the matrix itself. But of course, you have to respect that it is multiplicative. It is possible to multiply them. You know that matrix In, what was matrix In? It is a square matrix of order n. You have 1 all the time here, and you have zeros here. So that is the identity matrix. So if you take a matrix and multiply it by the identity matrix, it will not change the matrix. It becomes the same matrix itself, if it is possible to multiply that. Of course, this is also very important relation. If A is a square matrix, I is also, of course, I is always a square, but of the same order, then A times I is I times A, and it is equal to A. Okay? So if you don't mind, let us just have a proof, because the proof of this theorem is extremely simple, because all the entries on this matrix is 0. But if you don't mind, let me try to prove, for example, this. We take an A to be an n by n matrix, and then In, and I want to show that, for example, this A times that In is A. Of course, we can prove the other way around as well here. So remember again, even though the matrices are not commutative, but if you have I, it is commutative with every matrix. So I times A and A times A are different, are the same, sorry. Okay, so let us try to prove that. Why do you think this is the case? So my goal is to show that A times I is equal to A itself. Let us consider that A is n by n and I is of order n. Is it possible to multiply them? Yes, because this is n by n. I multiply A n by n from the left to this matrix, so it is possible. But I want to prove that this becomes the same A is. First of all, this is a matrix on the left, this is a matrix on the right. I want to prove the equality of two matrices. I have to convince myself the orders are the same, but which is very simple. If I multiply this by that, what will be the order at the end? Because when I say In, I mean In by n. And when I multiply this according to the rules of multiplication, these two will cancel, and what is left is an m by n matrix, which is of the same order. So from order point of view, everything is clear. But I need to show that every entry of this is equal to the entry of that. the corresponding entry of that. So I would say let I be a number between 1 and m, the number of rows, and let j be a number between 1 and the number of columns n. Of course, here I and j are natural numbers. We show that a times I, entry number ij, is equal to entry number ij of the same matrix, of the matrix itself. We show that. This is the question. We want to prove this. Yes? So how should I prove that? I need a sigma definition. Do you remember what was the sigma definition of the product? The product, this starts with this. This is a sigma because I am interested in one single entry of the product. One single entry of the product is defined according to this sigma definition. Do you remember? I have a little a. So let me write it like this. I have a with two indices here, and then I have I with two indices here. Do you remember how we fill it up? So I have a counter for my sigma, which always starts from 1, but in this case it goes up to, do you remember how to write it? So k goes from 1 up to the number of columns, up to this number which is in common, yes? So it goes from n, and do you remember this one starts with the I index, so let me write it here for you. So that was not a good way of writing. So I'm just talking about this. The ijth entry of the product is the kth entry of matrix A multiplied by k jth entry of matrix I. Yes, that was the definition. Do you remember that? Yes or no? At least you have a clue about it. Okay. But there is something about this. Do you remember something about this? K jth entry of matrix I. It is chronicle delta, yes? So it is delta k j. What was chronicle delta?
Oh, the identity matrix.
No.
The definition.
What's the definition of the chronicle delta? It is 1 if k, the indices are the same, and it is 0 if the indices are not the same. Yes? Okay. And then we had this for, okay, so this I am running k from 1 to n. At some point I reach k reaches to j, because j is already a fixed number between 1 and n. When I start running k from 1 to n, definitely at some point I reach to j value. For that particular value, delta becomes 1. But for the rest of the indices, delta is 0. So only one term survives from this. So this becomes what? A, I, j. Yes? So I don't know, you have forgotten probably a lot of things you have to review, but this we had before. It is a very, very simple calculation. So what I showed is that if you take ijth entry of this product, it becomes exactly equal to the ijth entry of matrix A itself. So every entry of this matrix corresponds with the same entry of this matrix. So this means that these two matrices are indeed equal. Okay. Okay, now let us go to the next page. For example, this is just examples. So you see that I have taken a matrix, which is 3 by 2. But what is this matrix? It is an identity matrix of order 2. Okay, is it possible to multiply them in this order? Yes, because this number 2 and this number 2 match. And then you don't need to be worried because you are multiplying a matrix by an identity matrix. Of course, you can take this row multiplied by this column, this row multiplied by this column, and continue. But as soon as you see that identity matrix involved, you don't do that. The answer is the matrix itself. And here you have the identity matrix 3 by 3. You see 1, 1, 1, everywhere else 0. And then I am multiplying from left to this matrix. Is it possible to multiply? Yes, because this is 3 by 3. The next matrix is 3 by 2. So it is possible to multiply. But I don't bother to multiply with that because the answer will not change. The answer will be the matrix itself. And this is for the case that I have a square matrix of order 2, so it doesn't matter. So it's important to remember, because in general it is not possible to commute, but when it comes to identity matrix or the zero matrix of the same order, you are allowed to commute. Yes? So remember these groups of matrices that are commutable. By the way, commutable is not the word we defined this before, it's commuting. Okay, that's it. Another simple theorem is this theorem. So if you have alpha, which is a number, and then you multiply number by matrix A, it becomes a new matrix, and then you want to multiply it from the left to this matrix B. So this number A is floating, can float around. Yes, you can put it here. If you want to, you can move it and put it next to B. If you want, you can pull it out and put it behind the product. So in that case, you really don't need any pairs of brackets, because it doesn't matter how you prioritize this multiplication, the answers will be the same at the end. Okay, and by the way, so from now on, 2a minus 3b can be written as minus 6ab, but you cannot write it as minus 6ba, be careful. So when you have matrices involved and you do not have any prior information about commutativity of those matrices, you have to respect the order. But why do you understand that this is the consequence of this theorem? I don't want to prove this theorem. Probably you can work a little bit on it yourself. It is not hard. So why this is true? So in principle, if I want to use this theorem to prove this, I have to go through different processes. So for example, we want to show that y2a times minus 3b is equal to minus 6ab. Why is that? For example, I don't know, you can consider this as a new matrix. Yes? And then you have minus 3b. So what do you have? You have this matrix A multiplied by minus 3b. But I just told you that minus a number can float around. So instead of putting minus 3 here, I can pull it out and put it here, yes? And now what is the name of A? A is this matrix. So this becomes minus 3, and then it becomes 2A, and then it becomes B. So you see, I have used that property in the theorem once. How? By floating this minus 3 from here, moving it outside. Now I put this name back, and then I can use that theorem again. So instead of putting this 2 here, I can pull it out and write it here. But again, this number 2 can go out. But no one writes so many things, okay? You can simply just multiply. But I want you to understand this highly depends on that theorem we proved, okay? Okay, but the situation is not that bad, because even though we lose commutativity, but fortunately we have distributivity. Okay, so distributivity means if you have a matrix M, and if you have the sum or difference of two matrices, and you want to multiply M by the sum or the difference, you can multiply like polynomials, yes? So you can multiply M by B, you can multiply M by C. If it is plus, you put plus. If it's minus, you put minus, yes? So that's distributive. But of course, it should be multiplicable, yes? I mean, for example, M, if M is M by N, then B and C should be of the type N by P, for example, both of them. Yes, so if M has N columns, B and C both should have N rows. If that is the case, then you can use distributivity. And distributivity, it's important. In numbers, I don't care about the way that I distribute. Here I am distributing from left. Here I am distributing from right. And it is important. For numbers, it doesn't matter, because if I have m times m plus b, of course, it is clear that this is equal to ab plus b times m. But for matrices, there is no guarantee that this product and that product are the same, even if this is m, for example. You have to be careful about that. So we have two versions. So this is extremely important. Let me go back to the board. So here, if you take a matrix A and you want to multiply it by this, assuming that this is possible to do, you cannot just write B times A plus A times C. This is wrong. In numbers, it is correct. You can write it that. But in matrices, you have to respect the order you multiply. So this is the lesson that you have to have in mind. Okay? And that is actually the content of this remark. So just let me read it. So note that if m, b, and c are real numbers, then since multiplication of real numbers this is wrong, is commutative, m times b plus or minus c can be written as this, as well as this, or any other combination that you like. But in matrices, you have to respect and write it only in this form. Okay? So let us just play around a little bit about with the notion of distributivity here. So for example, what can I write for this? Can I distribute it? Yes. So if I want to expand that, I have to distribute A by C, A by minus D, B by C, B minus D. So the answer is just simply AC minus AD plus BC and minus BD. Yes? So you can distribute. I want you to understand I am using this theorem 2 times or 3 times. This is important because here in the main theorem I have one single matrix. I want to multiply it by the sum of two matrices or the difference of two matrices. This is not exactly the same because here I have the sum of two matrices. I want to distribute it here. You need to give this a name, M, first in your head, and then it becomes MC minus MD. Yes, so I use distributivity once, and then replace M with A plus B. I want you to understand these details, yes, minus A plus B times D. So here I use distributivity from the left, but here and here I use distributivity from the right. So one distributivity from the left and two distributivities from the right are involved to do just this simple multiplication. I don't want you to do this. I just quickly do this myself, yes? But I want you to understand one distributivity from the left and two distributivities from the right are both involved to be able to do that. This is important to understand. This exercise, I like it, so I want you to understand it quite well. Because I have asked you to factor out matrix A in each one of these expressions. Okay? I want you to learn that. This is important. So you know that, by the way, when I say distributivity, I also mean factorization. Yes, when you say M times B plus C is equal MB plus MC, if you read this equality from left to right, it is distributivity. If you read the same equality from right to left, it is factoring M out. Yes, so that's the same thing. So if you go from left to right, you are distributing. If you go from right to left, you are factoring M out. Okay? So now in this exercise, I want you to actually factorize if possible. Okay? So for example, let us see. Is it possible to factorize something here? Is it possible to factor A out? Yes. So what is the answer? It's A times B plus C. This is possible. Okay? Now number 2, is it possible? So you have to factor from left. A appears on the left, A appears on the left, yes, you can factor, but if you factor, you have to factor from the left. If you just naively write B plus C times A, that is wrong. Okay, that is important. That's the only thing that you need to be careful. Can I factor A out in this problem?
Yes.
Yes, but I have to respect to factor it from right, because B appears on the right, A appears on the right, A appears on the right, so it is possible to factor it out, but you have to write it in this way. You have to write B minus C and then multiply it by A. For example, about this, can I factor something out? No. So this is important. If they are numbers, if I have AB plus CA, of course I can factor it out. I can factor A out and write B plus C. For numbers, it is possible. But for matrices, it is not possible unless you have a good reason that these two matrices commute or these two matrices commute. Is that clear? So this is possible factorization from left. This is possible factorization of A from right. But this is in this form because if you read the question, there are not any information regarding commutativity of matrices. So I would say no, I cannot factor something out. Okay, so let me just do this one on the board. AB plus BA. AB plus A. Can I factor something out? So for example, yeah.
Could you make it to A times B plus I?
Yes, but that's the important thing. So because, by the way, what can I write? I can write it as AB because for A, if you read the problem, I have written that all of them are square matrices so that you don't bother about being possible to multiply. So when I want to write A, because A is a square matrix, I can write it in two different ways. I can imagine it as A times I. I can also imagine it as I times A. Which one is more suitable here?
First one.
The first one, because this one, A lies on the left. I want to factor A out. So instead of this A, I write A times I. So this is important. So the first step, you write AB, and instead of A, you write AI, and then you see that I can factor A from the left. And this is important that I is left. I have seen some students might think that you just simply factor A out and write 1. That is not correct, you see. If you write something B plus 1, it doesn't even make sense. Because this matrix is B is a matrix, you cannot add a matrix to a number. So that's crucial that you have to write I there. Yes, is that clear? Okay. Let us go back to the slides here. So can I factor something out here? BA minus 3A.
Yeah.
So again the same story, okay? So BA minus 3A. So what is the answer? How should I do that if I want to write all the details?
Is it B minus 3A times I?
But
sorry.
A should be on which side?
Right side.
Right side. So this you cannot change here. You have to follow this. But for writing A, you have two options. AI or IA. Which one is suitable for this problem? I have to choose AI because IA because A here is on the right. So instead of A, I will write 3IA so that I have A on the right. And be careful. If you take A from the left, that would be wrong. You have to take A from the right. So this becomes B minus 3I multiplied by A. Yes? Okay, so for example, I have written one more example exactly below it. So instead of having a BA minus 3A, I want you to feel the difference. I have written BA minus 3A. Can I still factor A out in this problem? Yes, but I have to respect the direction, yes? Instead of this A, which one is suitable now? AI or IA? AI, because I want to have A on the left, yes. Because A here starts on the left, For this one, I want to have A on the left as well. Yeah, so this becomes 3AI. And then A here is on the left, A here is on the left. I can pull it out, so it becomes B minus 3I. So be careful about this. They are not the same. This is A times B minus 3I. This is B minus 3I times A. And there is no guarantee that these two are the same. Because this is one matrix, this is another matrix, there is no guarantee that these two matrices commute. Yes? Okay, I want to wait for you to do this for me. Okay, take as much as possible you can here out. I want to factorize this as much as possible. The same story here. I want to wait a little bit for you so that you can do number 7 and number 8. Okay. So can I factor something here? Yes, if I want to do it optimal in an optimal way, how many factors of A I can pull out?
Well, 2, 1 from each side.
Yes, so that's important. You take this A pull it out from the left, and you take that A, pull it out from the right. Yes, so the answer becomes what? I have A, and I have another A here. So I pull these two A's out. What is left is B. I have minus. I pull these two A's out. What is left is C times D. So that's what we can do. What about number 8? Yes?
You can pull an A out from the right.
From?
From the right.
From the right. Is it possible to pull it out from the left?
Yep.
This is possible, I think, in 2. But you also can factor a 2 out. Because I want to maximally factor it out. Yes? So what happens? So you can interpret it in 2 ways. Yes? You can say it is 2A, BA plus 4AI. Instead of this A, you can imagine it is AI. You can also imagine it as 4IA, because that's also A. If you think in that way, you can pull a 2 and A, this A, out from the left. What is left is BA, and then this is, what is left? 2I. But if you interpret it in that way, which is also correct, but you have to pull this A out, not that A, but from the right. So I put an A out from here. Usually we write numbers on the left, so this I want to respect here as well. So numbers can float around, it doesn't matter. Usually we prefer to write numbers on the left hand side. So 2 is pulled out, but this 8 is pulled out from there, so AB is left. And then you have plus, A is pulled out from the right, 2 is pulled out here, 2I is left. And I hope that you see that they are different. There is no reason that we believe that this is equal to this by looking at it, but they are equal. Why? Because if you distribute, both of them become the same expression. Okay, so sometimes they say that, okay, prove that this matrix is equal to that matrix. You cannot say that, okay, because they are the same combinations, more or less they are the same. No, because if you distribute them, after distribution, you get this expression. For this one, after distribution, you get the same expression. So because of that, they are equal. Yes? Because we cannot say that, okay, here A, B, and BA are not equal. We know that in general, of course. So is that understandable? Okay, but one thing we haven't done to prove that we haven't lost distributivity. I just told you that this is a theorem, but we haven't proven that yet. But let us just prove it for one of the versions. For example, distributivity from the left. Because I want to prove the theorem. Okay, so here, so I have a matrix M, I have a matrix B, I have a matrix C. So let us assume that this matrix is M by N. Let us assume that this matrix is N by P. The order of this matrix also has to be N by P, because I want to add them. So they have to be of exact same orders. Yes? So my question is that why this is true. For example, let us consider the plus sign. I want to show that this becomes MB plus MC. Okay? So don't look at these orders here. We want to multiply m by, I want to show that this sum is equal to that. Okay? So the first thing that comes to mind, if I ask you what is on the left-hand side, you would say that this is a matrix. What is on the right-hand side, that's also a matrix. If I want to prove that two matrices are the same, I have to convince myself, first of all, that the orders match. Okay? So what is the order of the total matrix on the left? Okay, I have an n by p matrix. I add it to another block of n by p. What will be that? It will be a matrix exactly of the same order n by p. And then I have this matrix m by n that I am multiplying it from the left to a matrix which is n by p. So what would be the final order? Yes, an m by p. Yes, the final order of the matrix on the left is m by p. And you can immediately convince yourself that's the case here. Why? Because this is m by n, b is n by p. When I multiply just these two, it becomes m by p. So this is m by p. For the same reason, this is also m by p. I am adding to m by p matrices, so that also becomes m by p. So from the order point of view, they are exactly the same. So what I want to prove is that every entry of the matrix on the left matches with the corresponding entry of the matrix on the right. Okay, so I would say that let I be a number between 1 and m, and j be a number between 1 and p, because I know that the final order is m by p. Then, okay, I take m by b plus c, order number I, j. Okay, so this is, I want you to help me to write that sigma. Because if I am interested in writing one single entry of a product, there's only one thing I can do. I just use the definition of the multiplication. So remember, this is a sigma. Every sigma contains a counter, and it starts from 1. And then you need to write the first matrix with some indices. I want you to fill it up for me. And then the second matrix, which in this case is b plus c, with two indices that I want you to fill it up. So there are two indices here, and one number on top. Okay, what are they? First of all, what is the number on top here? It is n, yes, because this matrix is n by p, that as a whole, and this matrix is m by n. So the number of columns and rows that are matching is n. So it goes up to n. The first matrix, do you remember, always starts with the row index. So it starts with I. And the second matrix ends with the column index, which is j. But what is the indices? What are the indices here and there? K, which is the counter of the sigma. Yes? So this is the definition of the multiplication. But I can continue this sigma. So I just write sigma k goes from 1 to n. I keep the first term, ik. But can you write something for this? Let us understand that. What is the meaning of this? It means that you add two matrices first and pick up the kjth entry of the sum. But how can I do that? I can do it in a different way. I can go and take the kjth entry of the first one, kjth entry of the second one, and add the entries. So this means that I can write it as kjth entry of the first matrix plus the kjth entry of the second matrix. Yes? Is this decomposition understandable? Okay. But now, do you think I can distribute this in? Because my goal is to distribute. Can I do that? Is it a circular argument, or can I do that here?
Yes.
Why? Yes?
Because you're distributing over numbers.
numbers. These are numbers, yes? This is one single number. It's a M is a block of numbers, but when I am looking at one particular entry that's just a number, it's a number, it's a number. I don't know that distributivity works among numbers, yes? So here I am distributing, but don't fall into this trap that this is a circular argument. No, it is not, yes? So K goes from 1 to N. I distribute it here, M, I, K, multiplied by B, K, J. Let me put the brackets here, and then plus M, I, K, C, K. I want you to understand it is highly non-trivial, yes, because matrix multiplication is a little bit complicated process, and then you see that still there is no guarantee that we have distributivity, but it shows that it is possible. But at least it is something clear. If I succeed to prove this, distributivity of matrices highly depends on distributivity of numbers, yes, because I use the distributivity of numbers. Okay, what do you think will be the next step? Look what I am going to reach. I want to reach somehow to the right hand side. So what can I do now? What is the next step coming, do you think? Yes?
Could you write MB and then these brackets?
Not yet. There's one step before that. So I have a sigma of two expressions added. I can decompose my sigma over the first plus sigma over the second, yes? So this becomes sigma over the first plus sigma over the second. Now what Sarah said is correct, because now this has exact correct form. You see, here I had this, I wrote it in the form of a sigma, but do you think that this sigma has appropriate form to be written as a product? Yes, because check. I have a matrix involved here with two indices, a matrix with two indices. This index in the middle is important to be the counter, which it is. And of course, and that's it. What can I write for this? I can say that this is M, B, which entry? AJ entry, IJ entry. Yes. So instead of this sigma, I wrote it like this. If you want, you can just do the reverse process. If I gave you this, you would be able to write it like this. Now I'm doing it the other way around. Okay, and then the same story here. It has exact right form that I need. I have the middle indices to be the counter of the sigma. Okay, so this becomes MC IJ. Yes, but it's not finished yet. There's one more step. Yes, this is ijth entry of this matrix plus ijth entry of this matrix. What can I write? I can write this is equal to the ijth entry of the sum of these two matrices, yes? And now it is finished. Why? Because I started from here. Ijth entry of this matrix is exactly equal to the ijth entry of this matrix. So this means that entry by entry, I can prove that all of them match. And it is important to see that it depends highly. If I lose distributivity of numbers, of course, I will also lose distributivity of matrices. Any questions? So remember, we lost commutativity, but the good news is that we didn't lose actually distributivity. Another thing that we don't lose, fortunately, we do not lose associativity. Okay, so that's the content of the next theorem. Any questions here? By the way, I have one exercise for you. I want to wait for you so that you can solve it for me. Yes. I want you to do example 1.95. Okay? I want to wait for you. So this is one of those problems that I engineered the numbers a little bit, okay? So it's very simple. Okay, so I have written the question on the board. So We don't know A and B, but we know that they are square matrices of order 2, and what we know is the product of them. Okay? Using that piece of information, I want to simplify this as much as possible. So what should I do? Yes?
You can factor out an A on the left side. And
Yeah,
B
so
on
that
the
was
right
actually the idea. Yeah? So what we do, we factor A. I just told you, because might be one impression is to find A and B. And I don't think it is possible, because if you say A, how many unknowns are there? There are 4. Is any entry, because we don't know anything about this A. And the same thing here for B. So there are 4 unknowns here as well. Yes? So in total, how many unknowns I am facing? 8. And then how many equations will I get from this one? How many equations, how many information I have from this one single equation? So remember, you have 8 unknowns, 4 entries for A, 4 entries for B, all of them are unknown, potentially. And then I have this equation. This is apparently one equation, but it gives more information regarding the entries. Yes? How many informations I have, how many equations I will have at the end? 4, exactly, thank you. So why? Because this, after multiplication, this becomes a 4 by 4 matrix. If you actually suffer a little bit, write them in terms of letters, and then you multiply them. At the end, you get a combination of algebraic expressions for each entry. So you will have 4 entries. You equate it with this one, you get 4 equations. But the number of unknowns you have is 8. So there are much more number of unknowns than equations. So apparently it is not possible, if you want to go in that way, to find A and B. Yes? So this is not working. So another way of thinking is that, okay, now I realize that I have both A's on the left and I have both B's on the right, and we have practice in factoring things. Yes? So what I do, I factor here. And this is why I told you this is one of those problems that in general we shouldn't be able to solve it. But I engineered these numbers in a way that you can do that. Okay? So what is left from this expression? I pulled these 2 out, so this is left. And then plus what is left there. Okay? But this we can do. But it still seems useless, but let us see what happens. What happens now? If 2 added minus 1 is 1, minus 1 added to 1 is 0, 3 minus 3 is 0, 5, oh, this is minus 4, sorry, I forgot to write minus. It is. But what type of matrix is this? It is very famous in matrix theory, yes? It is I. And what is the answer? By the way, I have been a little bit careless, because you know that I am facing multiplication of 3 matrices, so associativity is involved, but associativity is coming next, so I was a little bit sloppy when I wrote this. Because when you have multiplication of 3 matrices, there is still no guarantee that the order of grouping doesn't matter. But anyway, what's the answer? It is AB, yes? I times B is just B, A times B is just AB. But this, I told you that I engineered these numbers that you get this. Otherwise, you couldn't do it. And AB is this matrix. So the answer is actually the same. We got that, yes?
Is it possible in this specific question to write AB on the left side and then the added matrices on the right side?
No, that's impossible, because I don't know if you want to put AB on one side, it means that you are interchanging these 2 and you are interchanging these 2. But we don't know, is it possible to interchange these 2 matrices, yes? It's not possible, it's the only way that you can do it. Okay, so I was a little bit sloppy. And then I told you, so we didn't lose distributivity, and this theorem shows that we are lucky we don't lose associativity. Otherwise, matrix theory would be probably not that interesting, because if you're supposed to lose everything, then what is the point, yes? It is good to lose something, but not everything, yes? And then you will still work hard to gain something, yes? Yeah. Okay, Sorry, let me go back to slides here. Yes. So the theorem tells you that if you have three matrices, so in the way that I read it from left to right is A, B, C, assume that A, B, and C have some appropriate orders. For example, let us assume that A is m by n. Let us assume that A is m by n. Let us assume that B is n by p, so that A times B is possible. And let us assume that C is n by p, so that after I multiply them, which becomes m by p, sorry, this is not correct. It should be p times q, so that when I multiply these two, the answer becomes m by p, and m by p is multiplicable from the left to p by q. So assuming that the orders are in order, actually you can multiply them. But this is not trivial at all, that if I multiply AB first and then multiply the answer to C from the left, it becomes exactly the same thing if I multiply B and C first and multiply A from the left. Yes, I'm sure that I have already done that example, but let me just try to motivate you again here. It is not trivial at all. So for example, let me just take random matrices here. So we have A, which is 1, 2, 3, 4, for example. B, let me just randomly write the numbers. 5, 0, 2, minus 1. And C is 1, minus 4, 7, and 1. Just randomly, okay? Let me see what is AB times C. Okay? So to do this, I have to multiply A by B first. Okay, so let us just do it in our head. So C is just the C, I copy and paste it here. Yes, I copy and paste it here. And then, what is AB? You can do it in your head. What is AB? The first entry. What is that? Come on. Yes. This row, these columns, this row by that column. What's the answer? 9. Yes. 5, 4, add 9. What's the next one? Minus 2. What's the next one? 23, yes. 3 times 5, 15. 4 times 2, 8. Add 23. The other one is minus 4. Okay? And then you see, this matrix that you see, if I have given you this matrix from the beginning, it is probably not easy at all to guess that this matrix is a product of those two matrices. If you do not see the names, you think that you are multiplying these two matrices. Okay, and let us just do that. What's the answer? I take that one and multiply it here, which becomes 9 minus 14 minus 5, minus 36 minus 2 is minus 38, 23 minus 5, and this becomes what? Minus 93, so it is minus 97, yes? No. 96, yes? 23 times minus 4 is minus 92, do you agree? And then minus, so it's minus 96. But remember, after the first step, you are multiplying completely different matrix that you even couldn't predict that is going to happen. This matrix has not very clear relation with the matrices that I started with. Okay, but let me calculate the other way around. I copy and paste A this time. But let us do multiplication of B by C. So this time I take these two rows and these two columns. This row by that column. What is the answer? 5. That row by that column, the answer is minus 20. And then this row by that column, the answer is minus 5. This row by that column, minus 8, minus 1 is what? Minus 9. So I hope that I haven't done something wrong. You see, in the intermediate step, we are multiplying completely different matrices, yes? Because after the first step, I am multiplying these two matrices. Here, after the first step, I am multiplying these two matrices. This matrix is different from both of them. This matrix is also different from both of them. And the matrix multiplication is a little bit involved process. So it is not guaranteed that the product of those two matrices is exactly the product of these two matrices. I want you to understand it is not trivial at all. Yes? So, but hopefully, if I haven't done any mistake to spoil the joy. So what is the answer? Can you see that this by that? What's the answer? 5 minus 10 minus 5. And then I multiply this by that. It's minus 20 minus 18 is minus 38. And then 3 times 5, 15, minus 20, minus 5. And then finally 3 times minus 20 is minus 60, minus 36 is minus 96. It was, I want you to feel it. By this simple example, you really feel that it is cannot be something like a coincidence every time, yes? But we want to show that this is not really a coincidence. We don't lose this property and it holds. So it doesn't matter in which way you group them, but extremely important, the way I read it from left to right doesn't change. If you forget about pairs of brackets, I read A, B, C. On the right hand side, I also read A, B, C. Okay? Can I conclude something like this? This is not associativity. This is associativity and commutativity. Yes? Because associativity only allows me to take this pair of brackets and put them around the first two. But if I want to go from here to here, I have to be able to commute B and A, which is not in general possible. Okay, but I want to prove this one as well. So why this is true in general? Okay, so let me just be clear. So what I have written in the theorem, so let me just summarize them here. Okay, so I have M by N, N by P, P by Q. Okay, so I hope that you agree with me that ABC in this form and ABC in this form both are of the same order. Yes? Why is that? Because if I ask you what is the order of BC, by looking at B and C, you say the order is NQ, N times Q, N by Q. And A is M by N, so the order will be M by Q. The order of the left-hand side is M by Q. Easily convince yourself that this is also the same order. So from the order point of view, I do not have any problems. So again, what I have to do, what's the final order? The final order is MQ. So I would say that let I be a number between 1 and M, and J be a number between 1 and Q. Of course, I and J are natural numbers. Then what happens? I go and take the ijth entry. This is a little bit more involved than distributivity. The writing the sigma, the correct sigmas. So how can I write this sigma? How can I write this as a sigma? So I open a sigma, I choose a counter, it goes from 1, which you feed up this. So what should I write on top here for this combination? What should I write? I have written the orders here. Don't look for anything. So these are the orders. Okay, what should I write on top? What is BC? BC, N by P, P by Q. So BC is N by Q. And A itself is M by N. So the number in common is N. So you just write N on top. Yes? Okay, and then you need to have a matrix A involved and your second matrix, which is of course BC, involved. Yes? Okay, and then you have to fill up the indices. The first one starts with the row index. This one ends with the column index. And then the middle index is K. That's the first thing. The hard part is that the second one is also a product. So it will involve a new sigma. Okay? This is a little bit different from distributivity. Proving distributivity is easier. But now don't get confused. Copy and paste the first parts, this one and that one. So K goes from 1 to N. And then I have A, I, K. But now I open a new sigma only for this one. I want to make sure that you really understand. What do you think I will write in front? Definitely, this is a product. I am interested in one entry. The definition starts with a sigma. A sigma needs a counter, but you cannot use the same counter as before. So I changed the name. I don't know, I can write L, for example. And L over it goes from 1, but tell me where to where? P, yes. Because B, you are multiplying B by C. The number in between is P. So it goes up to P. And then you have the matrix B involved and the matrix C involved. Okay, now if you fill up these indices, it is good exercise to refresh your memory about the matrix multiplication in theory. So, can you tell me what are the indices for the first B matrix here?
Is it? No. Was it KL?
Yes, it's KL. Why is that? Because you are writing this matrix. Here the row index is K, so you put it here. And the middle one is always the counter of the sigma, so that's L. Now can you tell me C as well? Yes? LJ, yes. Because L is the middle one, and then the J index is still the J index, so I just write J. Yes? Okay. And now the problem is that, can I put this inside the first sigma or not? This is, by the way, these are no longer matrices. They are just simple numbers. Yes? Can I flip this into the first into this sigma? Yes. Why? Because the indices are I and K, and the counter of sigma does not depend on I at all, on I or K. It depends on L. So that's a constant for this sigma. So I can flip it in. So this, let me write all the details here. So I just copy and paste the first sigma. So K goes from 1 to N. And then I flip the other one in. So L goes from 1 to P. And then in principle, I have to write it like this because I have already multiplied them inside, but then I want to multiply a third number in. So this means that I have to write it in that form. Oops. Is that understandable? So I flip this sigma, this entry in, but then I have to multiply what I flipped in to what I already had. This is the way we'll write. Yes? Do you remember we talked about this, that these two sigma notations can be interchanged? We already talked about this, so I will interchange them, but let me just keep it for the time being so that you feel it, why you need to interchange this. But here, can I use associativity here or not? Because I want to take this pair of brackets and put them around the first two. To do this, I need associativity. But associativity is guaranteed here because these are numbers. Okay? So this means that I can do that. So you see that again, I am using associativity of numbers. Otherwise, I will also lose that property. Okay. No, so that is wrong. LJ. Okay, let me ask you a question. Can I flip this out from the sigma or not?
Yes.
This one. Can I flip it out from this sigma?
No.
No, because this quantity depends on the counter of L, depends on L, which is the counter of this sigma. So I am not allowed to flip it out. Yes? It's not a constant for this sigma. So that is why I need to interchange them. But I was able to interchange them if you remember what I told you on the previous lessons. So if I have finite sums and double sums, then you can interchange the sigma notations. The order doesn't matter how you add them, yes? So what I do, this is the reason that I want you to feel that we need it. I didn't want to do it in the previous step. My goal is to flip this out, but I cannot flip it out from here. What I can do, I can write it as sigma k, I will flip these two. I would write L goes from 1 to P, sigma k goes from 1 to N, and in that I would write this. Yes? I interchange those sigmas. But now can I flip this out from this sigma?
Yes.
The answer is yes. Okay? I intentionally want to do it from the left. But you have this intention that you have this instinct that, of course, this C should remain on the right. I want you to see that you are forced to put C to the right at the end. Okay? But these are numbers. If they are numbers, I can do whatever I like to do with them. So I pull this out, okay, from the first sigma. So this becomes sigma. L goes from 1 to P. By the way, this is a very important thing because you have a lot of degrees of freedom. I want you to see whatever you do at the end, you are forced to keep the order. Okay? This I want you to see. But I want you to see that you immediately can pull this out from the first sigma, but not from the second sigma, of course, because it depends on L. So I will pull it out, and then what is left for me is sigma of this, and because this is alone, I don't need a pair of brackets anymore. It is not wrong if you do it, but I don't need it. Okay? Okay, now can you tell me how can I write this simpler? This kind of sigma should be familiar to your eyes, yes? What is that? So I copy and paste the first part. Okay, what can I write about that one that I actually circled around? Yeah, it is clear. It's crying out, what is that, yes? So we have used it several times.
Is it the matrix AB in the order of IL?
Exactly. Yes, exactly. Because that is the IL entry of the product of AB, yes? So that is AB, IL. This is the matrix AB. Yes? You don't need to do that. Matrix AB, IL. Okay. Can I interpret this sigma as a new product again? I want you to feel that because you see, this is not the appropriate order of sigma indices, yes?
Yeah.
Because you need to have the middle index the same, and that would be the counter. So then you have to, you see, I mean that if you don't respect there, at some point you have to force to reverse the order. And can I reverse the order? No matters because these are numbers. So this means that you need to understand there is no way to come up with CAB at the end. Yes? Because this is probably possible. You'll say to yourself, okay, this is a number, that's a number. You, Babak, might be have written it from the right. I prefer to write it from the left. So Babak will conclude AB times C. I will conclude C times AB. But no, this is not possible because in this form it is not following the order. We need to have these middle indices to be the same. Otherwise, you cannot write it as a product. But this motivates me. Okay, let us see the other way around. This becomes AB, IL, and then I have C, LJ. Is it in the wrong? Is it in the proper order now? Yes, yes. You see, by the way, I forgot to write P. Okay, so first of all, let us check. I have two indices. The middle index is the same, and that is exactly the counter of the sigma. So I can write it as what? I can write it as ijth entry of a matrix. Which matrix? This matrix on the one hand, multiplied by this matrix on the other hand. Okay, so what we have done, it was a long, actually, theorem. So we started from here, if you remember. So we showed that ijth entry of this combination matches with ijth entry of this combination. Okay? So that was an involved theorem, actually, and you see it is not trivial at all. But everything miraculously matched, so we got that result. Okay. Any questions? Yeah, we have a little bit of time, so let me just finalize this part, going back to notes. So let me read this remark for you. So according to last theorem, to multiply several matrices, it is not important which multiplication we do first, as far as we respect the order that matrices appear in the product. For example, let A, B, C, and D be matrices all of the same order. If I write A, B, C, D without any pairs of brackets, it is not ambiguous. How many multiplications are involved here in A, B, C, D? I multiply A by B once. I multiply B by the result by C2. I multiply the result by D3, yes? But it doesn't matter how you prioritize these multiplications. A, B, C, D, you can say that, okay, first I multiply A by B and C by D in parallel, and then multiply the results. You might say that, no, I want to multiply B and C first, and then multiply A and D. Or you might say that, okay, I don't know what I have written here. That's very strange. This is probably, I have to take it out. And then you can multiply it in this order. So, but not in this grouping way, okay? The order that I read is the same. A, B, C, D, 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 okay? But the way that I group them doesn't matter, okay? But again, but this is not, again, trivial for a mathematician. They have to convince that because the associativity involves three matrices. In principle, there is no guarantee associativity will work for 4 matrices or so, but you can prove them using mathematical induction. But what I want you to know that if you have a bunch of matrices multiplied without even any pairs of brackets around them, it is not ambiguous. It depends in which way you want to group them. The intermediate steps might be different from the calculations of your friend, but the final answers should eventually match. Yes? Okay, so let me see how much is left. Yes, there are questions. Okay, I will actually try to do one of them here today, and then one of them I will leave for you to do at home. Okay, so solve the following equation. I want to interpret everything yourself. First of all, just I want to see why this is related to associativity, because in principle, I couldn't write something like this if I didn't convince you that associativity holds. Because you might say, Babak, should I multiply these two first and multiply the answer, or should I multiply these two first and multiply the answer? You now know that there are no differences between these two. So you do it whatever you like, and you yourself interpret this 0. Is it a number? Is it a misprint? It should be a matrix there, or whatever. I want to wait a little bit for you to solve that problem for me. Thank you. Okay, did you get the answer? No one? Okay, I want to finish it because otherwise the lesson will not be finalized. So let us at least tell me, because I use sans serif fonts to denote matrices. This is quite common in recent books. So do you think this, I have written 0 as a number. Do you think it's a misprint or it should be, is it? Yeah?
Well, it could also be interpreted as the zero matrix.
Yes, but this is, I mean, if I write that 0 as a number, that's also okay in this case. Why? Yes?
The final matrix will be just one by one.
One by one. So then I told you that when it's a one by one, it doesn't matter if you show it with the matrix itself. Okay, so here you decide to multiply in any way that you want to. For me, because usually in the future linear algebra lessons, it is common that you multiply a square matrix by a column matrix. For me, that is easier to multiply this first and then multiply this here. But that's up to you. You can multiply these two first and then find the answer and multiply it there. So I want you to do the other way at home to practice this. So what I want to do, I would say that, okay, I will copy and paste the left one. I decide to group these together. We just learned that grouping doesn't matter. Okay, so what I do, I take and partition these two rows. I have only one column, so I multiply this row by that column. It becomes 2x. It becomes plus 4 plus 0, so that's just plus 4. This is one single entry. And then I will do the same thing with the second row and that column. So it becomes x, 0, minus 2. If I add them, it becomes x minus 2. And I will take this one and multiply it there. So this becomes 0, 2 times 4, 8. Keep it in mind. 4 times minus 1 is minus 4. 8 minus 4 is 4. Is equal to 0, supposed to be 0. And then I have one single row and one single column. I want to multiply it. So I know the matrix will be 1 by 1, so I don't bother to put the square brackets. The first row should be, the first entry should be multiplied by the first entry. The second entry should be multiplied by the second entry. And the third entry should be multiplied by that one, and I have to add them up. The answer is supposed to be 0. And then I solve this equation and find the value or values for x. And I think it's a quadratic equation. Might be there are two answers, I don't know. So this becomes 2x squared plus 4x plus 4x minus 8 minus 4 equals to 0. So 2x squared plus 8x minus 12 equal to 0. But then I divide everything by 2 to make it simpler. So it doesn't look to be a friendly number. Yes, we need two numbers whose sum is 4, the product is minus 6. I don't think we have them, so we just go to ABC4. We have them, but they are irrational numbers, so we cannot guess them. So I use the ABC formula. So x becomes minus b plus or minus the square root of this number to power 2 plus 24 divided by 2. So x, there are two answers, minus 4 plus or minus the square root of 40 divided by 2. I also prefer to simplify it because square root of 40 can be written, square root of 40 is 10 times 4, so this becomes minus 4 plus or minus 2 square root of 10 divided by 2. And then I can factor a 2 out and simplify it. Okay, can you confirm my calculation? Is it easy? Yeah. Did I?
No, here when you solve it in
At the end?
the doesn't it can no, that was my mistake.
No, a square root of 40 is 2 times square root of 10. But I was wondering, so Robert, did you get the same answer, Tino? Okay, the same answer? Okay, so that's good. Okay, so this is also simple, but I want you to understand we will not be able to solve this problem before proving to ourselves that the matrix multiplication is associative, yes? Because you might say that, okay, how do I know to group these two first? You can, for example, at home, if you want, you can multiply these two first. The intermediate step will be different, but the final answer will be the same. Okay, any questions? Okay, thank you very much.
Thank you.